Good morning, class. It is Tuesday, April 28th. Today's lecture and Thursday's lecture will be looking at hypothesis testing for two samples. So this week we're going to be interested in comparing two sets of data to compare them to see how different or similar they are in statistical structure. Before we do that, let me just talk about this week and next week. Lab 8 is due today by 5 p.m., just as a reminder. Also, this will be the last lab that I will assign, by the way. So there will be no more labs after Lab 8. Secondly, homework 11 is now available, and also this will be your last homework. This homework is 6 problems, and it's due by May 5th at 11:59 p.m. And just note, I'm sure some of you will want to start the assignment today. The first 2 problems will be based on today's lecture, and the remaining 4 problems will be based on Thursday's lecture. This way you can split it up and get some of it done and then come back to it later. Thirdly, test number 4 is a week from today, on May 5th. We will do this the same way we did test number 3, where you sign in at 11:30, open the test. It will be available at 11:30. It will be available for 2 hours, and you'll have to upload your solutions within that window of time. So you'll have 2 hours to complete the test. And just as a reminder, your NTSs that you complete are going to count as 40 points of that test, and the other 60 points will be selected problems. Now, as for the final exam, I still have not received word from Collin College about how we will take the final exam. So let's just say for now, if we don't hear anything from Collin College, then the final exam will be taken online on My Math Lab where you complete your homework. So I have not really decided exactly how I will design that exam, but I can tell you right now it won't cover the entire semester. I don't think that a full semester exam is a fair exam, especially for a class that's not in your major. I can understand if math is your major, then I think it's fair to test you on the whole semester. You should be a master of that knowledge if you're a math major. But I assume that most of you are not math majors, so a final exam covering an entire semester I don't think is fair or realistic. So it will be selected topics, which I will give to you on the day of our review. And the review will be next Thursday after the test. Okay, so Tuesday will be the test, and then Thursday will be the review. And the review will be just like this. It will be a video, and I will try to make it as short as possible. This way you have an understanding of how the exam will be done and what is expected. Okay, so now the goals for today's lecture. We will be looking at testing hypotheses for a population mean from paired data. Okay, so again, we're going to be testing a population mean from paired data, which means you have 2 samples of data that get paired together. So you have X data and Y data, and we pair them together like this, X comma Y. And then, of course, like before, we'll construct and interpret the confidence intervals of those paired data. So this is something new to you, paired data. Now, even though it looked like there was an X and a Y, it's not the same thing as graphing points. It's not that type of paired data. So first, paired data are X and Y together, can represent one group of persons or things that are measured twice. They are measured twice, okay? So here are some examples of what that would look like. So before and after studies. Are a classic example of paired data. So suppose you're going into a weight loss program. What they want to determine, in terms of the effectiveness of the program is the change in weight from before you started the program until the end of the program. So the before data would be your weight before you start the weight loss program, and of course after would be at the end of the program to see what your weight is then. So people might be interested in comparing those just to see if a weight loss program is actually effective or not. Another type of paired data example would be using 2 different measuring devices on the same thing. So for example, a police department might be interested in buying a new type of radar to measure the speed of cars on the highway. So they might be looking at different options. They might be looking at radar gun A and radar gun B, and one might be more expensive than the other, and they want to know, the price is different, but are the radar guns actually different? So what they would do is they would use both of those radar guns at the same exact time on the same exact car. And they would do that again for another car and another car. All right? This way you have those pairs of radar data that get applied to one car at a time. Okay? So you get two measurements on one car, and you repeat that process. You could also be interested in using two different conditions on the same thing. So you might be interested in braking distance on dry surface versus a wet surface. So you, of course, would have to use the same car and same set of brakes on a dry surface and a wet surface and compare the braking distances. All right, secondly, because we are depending on two measurements, x and y, that are taken relatively around the same time, we say that x and y are dependent samples. Even though they're separate measurements, we say that they are dependent because we're trying to establish whether or not there's a difference between them, but also those two measurements are taking on the same thing. They're taking on the same thing. So they are dependent on each other. Now, the main thing that we're interested here, statistically speaking, is the difference between the two measurements that are taken. So is there a difference between your before and afters, for example? So what does the word difference mean in mathematics? It simply means you subtract. So we'll call little d difference, and then we always subtract x minus y, all right? We don't really do y minus x, okay? So just keep that in mind, that when we have our data sets x and y, we will subtract x minus y to calculate the difference between those two values. Now, what other stats do we need for this? So A, we certainly need the differences between each x and y, which we just stated. So that's d sub I equals x sub I minus y sub I. And each I value corresponds to a data value. So when you have D1, that just means your first set of data values. So your first x value and your first y value get subtracted. That 1 could also correspond to person number 1. And then you're going to have a D2 and an X2 and a Y2 for person 2, and so on. Now, the mean difference, you're going to calculate a difference for each person. D1, D2, D3, D4, and so on. You calculate the average, and we call that D bar, just like X bar. And then the standard deviation of those differences will be called S sub D. This way we know that normally we have like S sub X, meaning the standard deviation of X values or data values. But here we're doing something different with the data values. We are subtracting them. So we're going to call it S sub D for the standard deviation of the differences, because we're going to be analyzing the differences. All right, so for example, so let's compute D bar and the standard deviation of the D values. So let's say we have this table here, and we want to compute first the differences. Well, simple enough. If you add another column or just do the scratch work on the side, you just subtract each x and y, just like this. So your D values are -3, 0, 3, 1, and -2. Okay? So now, on the calculator, how would you do this much on the calculator? Now, even though you really don't need the calculator to do that, you're going to get problems where the numbers are not so simple, and you might have a lot more numbers, okay? So it might be better to do this on the calculator from scratch. So here's what you'd have to do. First, you would enter in each list those numbers, right? So I already did that for you. Now, how do you get the calculator to subtract them? So what you would do is go to a new list. So let's use list 3. Now, notice I've highlighted the list 3. Make sure your cursor is up there, and make sure it's black like mine is. And now you're going to do second 1 minus second 2. Now, if you're wondering what that just did, take a look at the bottom of the screen, and it sets up a little formula. List 3 equals L1 minus L2. That's the equivalent of saying D equals X minus Y, right? Because list 1 are my X's, list 2 are my Y's, and in list 3, we're going to subtract those, okay? So this is like the equivalent of an Excel spreadsheet, if you've ever used that before and have written formulas in a spreadsheet. So now hit enter, And there you go. There's the numbers that are in my table there. All right, so what's the next step? So now we're going to use one-var stat to get the mean and standard deviation of list 3, right? Because we're using the differences to compute our statistics. So we want D bar. We need the mean of the D list and the standard deviation of the D list. So do stat, and then you'll do number 1, one-var stat. Change the list number to list 3. Hit calculate. Okay, and there's the numbers that you need. So D bar is the X bar, negative 0.2, and SX is SD, 2.39. Okay, rounded off the 2 places. Now, how come your calculator doesn't have D there? Your calculator will always have X's here no matter what your variables are. Your calculator doesn't know that we're calling this D. All right, your calculator will always call it X. Okay, next thing. What are the hypotheses that we would use for an actual test of paired data? So, again, we're interested in determining if there's a difference between the population X and the population Y. So we're really interested in that mean difference, that average difference between the two. So more specifically, we do that by determining their mean difference. So the mean difference for the population is called mu sub D. So we know that mu stands for the mean, D stands for difference. And the possible hypotheses are, and there's 3 sets. So the null hypothesis, remember, always has an equal sign. So we would say that mu D equals 0, and in plain old English, that simply means that there's no difference between X and Y, right? The mean difference is 0, 0 difference. And then the alternative, one possibility is having the not equal to symbol, and that's just the opposite of this, that there is a difference, that the difference is not 0. All right, number 2, that null hypothesis is always the same. So instead of, for the alternative, using not equals, what if we use less? So if you say that the mean difference is less than 0, what does that mean? So that means that data X is less than data Y on average. Now, in algebra, one thing we could do is we can move the Y over to the X by subtracting it from both sides. Okay? So if you do X minus Y, you get X minus Y is less than 0. And X minus Y is a difference. And we're looking for the average of that. So you could replace this with mu D, and it gives you this same statement here. All right, and then similarly, for number 3, the null is still the same. It's equal 0. And then here would be that mu D is greater than 0, which means that your data X is, on average, more than data Y. All right, and of course, if you bring Y over, that means X minus Y is greater than 0. So therefore, your difference or your mean difference is greater than 0. Okay? All right, C. The data in these problems typically are small in number, and also we won't know the population standard deviation sigma. So that means we're going to be using t-values to set up our problems. The test statistic, if we're going to use a test statistic method, remember that's called the classical method of hypothesis testing. When you use a test statistic, is this formula here, d bar minus mu d over sd over the square root of n. And then note, you might have noticed that in the hypotheses that mu d is typically 0, but not always. But the problems that we do will have 0 for mu d. So really, the formula will simplify to just d bar on top minus 0, or just d bar, over standard deviation divided by the square root of n. Now let's compare this to our test statistic from last week. It's the same format, just different lettering. Instead of x bar, we have d bar. Instead of mu, we have mu d. All right, and then of course s is sd. So it's the same exact formula, but just rewritten for the variables that we have in this type of problem. Okay, now also we're going to be using our calculator very much more so than actually doing stuff by hand. So, and again, since we're going to be using the t-test, we'll need program 2 and program 8 to do the p-value from the t-test and the confidence interval from the t-interval. Okay, so we'll be using that instead of the test statistic. We will do one problem though with the test statistic. All right, so let's take a look at example number 1 here. So in an experiment conducted online at the University of Mississippi, study participants are asked to react to a stimulus. In one experiment, the participant must press a key on seeing a blue screen, and their reaction time in seconds to press the key is measured. The same person is then asked to press a key on seeing a red screen, and then the reaction time is measured. So the result for 6 randomly sampled study participants are as follows. Okay? So the first thing I would do in this problem is do stat and number 1 edit and just type in the 2 list of data. We'll come back to that. Now what we're going to do is just assume that blue is X and red is Y. And it usually goes in that order. Your first set of data is X, your second set is Y. And we would just like to know that for each person, if there's a significant difference in the reaction time based on the color of the screen. See if color affects behavior or thinking. All right, so now, the first question I gave you there is question C from this problem. We're skipping A and B. We want to know, is the reaction time to the blue stimulus different from the reaction time to the red stimulus at the alpha equals 0.01 level of significance? And you can ignore that note there. We don't really need to pay attention to that. So again, remember blue is X and red is Y. So what do we want to first write down? How about our hypotheses? Remember, blue is X, and we're saying that the mean difference is just different between the 2 groups. That blue is different from red. So that simply means that your first set of hypotheses, not first, your only set of hypotheses, are these. All right, that the mean difference is 0, meaning that there is no difference. And then for the alternative hypothesis, different just means that they're just not the same. So we would use mu d is not 0, that the difference is not 0, that there is some kind of difference. Okay, so now the next thing we're going to do in this problem, we're going to do both approaches just to practice them. And I would like you to write these down on your NTS. Don't choose one or the other. I'd like you to write down both. It's good practice. You'll need to know it for your test. So we're going to do the p-value approach and the classical approach. So in order to do really either of those, we do need to use the calculator to run this. So first thing we need here are the differences. So second 1 minus second 2. And then you hit enter. And then it just subtracts the 2 lists for you. All right, so list 3 is what we need to perform this test. So now, let's go to stat and tests, number 2. And since I already have a list in there, we're going to click on data, because see, it gives you an option here to type in the list itself. All right, so mu null is 0, right, from the null hypothesis is 0. List 1 is the wrong list. It's list 3, or where my D values are. The alternative hypothesis has a not equal to symbol, so you choose that. And remember, you have to choose the right one so you get the correct p-value. And then we're going to hit calculate. Okay, and the p-value is the third number down. So there we go. So 0.2466, or however you like to round. Now, how about for the classical approach? Let's take a look at that. So remember, the classical approach, you have to set up a bell curve. You have to find a number in a table that sets up the regions that correspond to the null and the alternative hypotheses, right? And then you have to get a test statistic to see in what region falls in, okay? So first, since we're using a t-distribution, the alpha value is 0.01. The alternative hypothesis tells us that this is a 2-sided test. So remember, alpha has to be divided by 2. So that gives you 0.005. All right, so 0.01 divided by 2 is 0.005. Okay, the degree of freedom is 6 minus 1. Remember, there's 6 people in this study, so 6 minus 1 is 5. And these numbers here are just the numbers from the table. Remember, you have to use the t table to find that. So here's 0.005. Here's the 5th row, and there's the 4.032 that I have in the graph already, okay? So remember, the middle is HO, and then the ends there, that's where I would reject HO, or my alternative hypothesis would not be rejected. So next thing, what's my test statistic? So here's the formula. You plug in the numbers that are your D bar, your SD, the N, and you get 1.31. Okay? Now also take note, I want to show you real quick, a little quick way to actually get your answer there. If we go back to the program we just ran and run it again, notice the second number in the list there, there's your test statistic also. So you don't really have to write down the formula because the program gives it to you already. Okay, and also notice it gives me the X bar, the standard deviation, and the N. So it gives me all the stuff that I needed for the test, or numbers that go into the test. All right, so now what do we conclude here? All right, well, first off, this number here is in where HO is, right? So it's not in the HO rejection area. It's here in the middle where we do not reject HO, right? And also the p-value is more than my alpha value, right? 0.2466 is more than 0.01. So we do not reject the null hypothesis. But you must write a sensible conclusion. What does it mean to not reject the null hypothesis? So what does this translate to in plain English? That there is no difference. All right, there is no difference. So more specifically, all right, the two different stimuli may not be different. Okay, so there's no mean difference between the two stimuli. So therefore, the two different stimuli may not be different. Did I write timuli? Oh well. All right, question D. How would you do a confidence interval for this? Well, since the calculator is already set up, we would do stat and test and number 8. Okay, so we have list 3 in there. And the confidence level, let's see, 99 and 99, that's correct. So we plug that in, just hit enter, and there you go. So there's the confidence interval. Now interpret it. So we would first, remember, you have to take the null value and just see if it's in the interval or not in the interval. So 0 is in this interval, right, because it goes from negative to positive. So 0 is somewhere in the middle. So that means we do not reject HO again. Now, what does the interval interpret? So the interval estimates that the true mean difference between the stimuli could be 0, because we're only really concerned about the number 0 here. 0 difference. And if 0 is in the interval, then the interval is pretty much saying that there is no difference. Okay? So when the interval goes from negative to positive, that's just another way of saying there's no difference. However, if the interval has the same sign, negative and negative or positive and positive, that means something else. All right, example number 2. So waiting in line. A quality control manager at an amusement park feels that the amount of time that people spend waiting in line for the American Eagle roller coaster is too long. To determine if a new loading and unloading procedure is effective in reducing wait time in line, he measures the amount of time in minutes people are waiting in line on 7 days. And after implementing the new procedure, he again measures the amount of time in minutes people are waiting in line on 7 days and obtains the following data. All right, so if you look at the data here, we have the wait time before this new procedure is implemented, and then wait time after will be Y, all right, the wait time after this new procedure has been implemented. All right, so this is like a before and after type study. So we're going to be looking at the question here. All right, is the new loading and unloading procedure effective in reducing wait time at the alpha equals 0.05 level of significance? Okay, so now what does that mean? So it simply means that we're just trying to determine if the before wait times are more than the after wait times. That's what it means that these times will reduce, right? That they were higher before and less after. So before would have to be greater than after. So that means your x would have to be more than y, or if you bring the y over to the other side by subtracting it, you get x minus y is greater than 0, which gives us our alternative hypothesis that mu d is greater than 0. Okay? So now the p-value. Well, since I gave it to you, let's figure out how we get that. So you'd have to go to the calculator and enter in the data. So there it is. And then you'd have to hit in the third list again, second one, minus second 2, hit enter, and now there's the differences that we need to run the t-test. So I'm going to do stat tests number 2. So my mean is 0, my list 3 is the correct list, but I need to change the inequality to greater, right, because the alternative is now greater. Now I calculate, and there you go. So that's how I got my p-value of 0.129. Here's my test statistic, so you could use that if we need it. But for this one, I'm only doing the p approach. So the p-value is more than 0.05, so we do not reject the null hypothesis. So now how about the confidence interval? So we would do tests and number 8. I got to change my confidence level, right, because my alpha is 0.05, which means 95% confidence is the appropriate level. Calculate, and there's your, all right, there is your confidence interval right there for, remember the interval is for mu d. So this is an interval which tries to estimate the mean difference between the before and after values. And what do we notice here? That 0 is in the interval again, right? So since 0 is in there, we're not going to reject HO. And once again, we're in a sense supporting that the mean difference is 0, which means in plain terms that there is 0 difference or no difference between the x and the y values. Now, in terms of the context of the problem, in terms of this roller coaster weight line, all right, we would say that the new procedure may not significantly reduce the wait time because there's no difference in the before and afters. Okay, they're about the same. All right, so our final example, number 3, a DUI simulator. So this would be a great problem, actually, for high school kids. So to illustrate the effects of driving under the influence of alcohol, a police officer brought a DUI simulator to a local high school. Student reaction time in an emergency was measured with unimpaired vision and also while wearing a pair of special goggles to simulate the effects of alcohol on vision. For a sample of 9 teenagers, the time in seconds required to bring the vehicle to a stop from a speed of 60 miles an hour was recorded. All right, so again, the numbers on top are just the students, student 1, under normal conditions, and then, of course, wearing the impairing goggles. Okay, so at alpha equals 0.05, determine if the brake times for unimpaired vision are less than the brake times for impaired vision, just to see if people can understand whether or not that there's a difference between sober driving and drunk driving, to see what the difference is. All right, so of course, first thing you want to do is enter the data. So I already have that done for us. And what are we interested in here? We're interested in whether or not that X, which is representing our normal driving, is less than Y, which represents drunk driving. Okay? Remember, and this just refers to the stopping times for those particular drivers. So now, since we're wanting to test that X is less than Y, then we're going to be using the less than sign in the alternative hypothesis. All right, so the null hypothesis, which I forgot the label here, this is H sub 0. So make sure you label that as H sub 0. And this is H sub A, all right, that mu D is less than 0. So now the p-value is very small. Let's take a look at how we get that. So you'd have to do, just as before, second 1 minus second 2 for your list 3. So there's the differences. And then we're going to do stat and tests, number 2, 0, list 3, and the less than sign, and you hit calculate. And there you go. See, the p-value there is 2 point da-da-da-da, but look at the end here, it has e negative 5. So that means you have to move your decimal place 5 places to the left. So 2 is one of those places, and then you need 4 more zeros to make it complete. So that number there is very small, and therefore it's less than alpha, right? That number is less than 0.05, which means we reject the null hypothesis that mu d equals 0. So now the confidence interval, same idea. You do stat, tests, and number 8. And the confidence level for this is also 0.95 because 5% was the error level, so 95 is the confidence level. All right, so there is the interval that I computed. And notice this time both numbers for the endpoints are negative. The lower number is negative, the upper number is negative. 0 is not in the interval. Okay? So the interval here is estimating that the mean difference is going to be negative. All right? Which is another way of saying that x is less than y. So we conclude, therefore, that the break time for unimpaired vision could be less than braking time for impaired vision, which certainly implies, hopefully, to the high school students that driving drunk is going to affect your visual ability to drive. Okay? Okay, so that is it for today's lecture. Remember, your NTS is due by 5 p.m. today. I will see you on Thursday. Everybody have a great day. Take care. Bye.